Now, how an AK-47 works. Invented by Mikhail Kalashnikov in 1947, in a testing shed in Kovrov during the winter of 1947, the frozen air carried the metallic scent of machine oil and freshly burned powder. Mikhail Kalashnikov stood alone, bent over a wooden workbench covered with tools, screws, and steel parts, still warm to the touch. Before him, resting on an oiled cloth, lay the prototype, a tool with simple lines, almost primitive. Light woodstock, stamped steel receiver, curved 30-round magazine, no chrome, no ornament. He lifted the device, felt its balanced weight, and examined the space between the bolt and receiver. 2 millimeters of clearance, maybe more. For any traditional engineer, this would be unacceptable. Precision meant micrometric adjustments, perfect fits, minimal tolerances. But Kalashnikov had learned something different on the front lines of the global conflict. He had seen equipment jam with a single grain of sand. He had held mechanisms that seized in the cold. He had collected captured foreign hardware, impeccably machined, that stopped working after 3 days in the mud of the plains. The prototype before him didn't follow that logic. It accepted imperfection. The parts had room to move even when dirty. The gas system isolated the chamber from residue. The stamped receiver, considered inferior by experts, could be produced in tractor factories. Everything in that design contradicted the orthodoxy of technical engineering, and that was exactly why it might work. Kalashnikov pulled the bolt back. The sound was rough, mechanical, honest. There was no foreign smoothness, no high-end refinement, only function. He inserted an empty magazine, cycled the mechanism 3 times, and observed the phantom cycle. Everything moved with controlled looseness. Everything seemed crude, but resilient. Outside, snow covered the testing ranges. Inside the shed, the dim light of a hanging lamp cast long shadows across the workbench. Kalashnikov knew that in the coming weeks, this prototype would be tested to its limits. It would be buried in mud. It would be left in snow. It would be operated thousands of times without cleaning. And if his intuition was correct, if the decision to design for reality rather than ideals made sense, then those generous clearances, that apparent lack of sophistication, would be exactly what made the system indestructible. He adjusted one last spring, wiped his hands on his apron, and positioned the hardware back on the bench. The definitive test would come in the morning. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Mikhail Kalashnikov was not an engineer in the formal sense. He had been born in 1919 in a Siberian village, the son of peasants. His family was relocated during the forced social shifts of the 1930s. He grew up understanding tools, simple mechanisms, and improvised repairs, the engineering of survival. At 18, he was called into service. He became a vehicle commander. In 1941, during the invasion, his tank was hit by heavy fire. He survived but spent months in recovery. It was during this time that the idea began to form. He talked with other injured personnel. All had the same frustration. The equipment they used was heavy, slow, or unreliable. Standard models were effective in close quarters but had limited reach. Other semi-automatic models were too sophisticated, required constant maintenance, and failed in adverse conditions. Meanwhile, the opposition used an advanced model that combined range, rate of use, and portability. The home nation had no equivalent answer. Kalashnikov began to sketch. He had no academic training. He didn't know advanced ballistic calculations, but he knew the people in the field. He knew what jammed, what broke, and what was abandoned because it was too complicated to fix under pressure. His first proposal was rejected. The second, too. But he persisted. In 1946, he gained access to an experimental workshop in Kovrov, an industrial city northeast of Moscow. There, surrounded by lathes, mills, and skeptical technicians, he began assembling the prototype now resting on the bench. The pressure was silent but absolute. A new global tension was beginning. The nation needed to re-equip millions. It needed mass production. It needed something that would work on the frozen steppes, in the dense forests, and in the central deserts. There was no time for complexity. There was no margin for fragility. The equipment had to be produced quickly, operate in any climate, and be simple enough for anyone to keep it running. Kalashnikov understood this instinctively. He wasn't creating a masterpiece of engineering to impress technical committees. He was creating a tool that needed to work when everything around it failed. Every design decision reflected this reality. The stamped receiver reduced manufacturing time. Generous tolerances permitted operation even with dirt. The gas piston system isolated critical components. The curved 30-round magazine balanced capacity and reliability. At the end of 1946, he presented the prototype to the commission. There was silence, there was doubt, but there was also curiosity. In January 1947, they authorized field tests. The explanation of how the AK-47 works is surprisingly straightforward. And it's precisely this simplicity that reveals its genius. When the operator activates the mechanism, the firing pin strikes the primer. The powder expands instantly, generating pressure that pushes the projectile through the barrel. But here's the critical decision. A small portion of the expanding gases is diverted through an opening near the front. These gases are channeled into a tube positioned above the barrel, where they press against a solid steel piston. The piston is robust, heavy, almost brutal in its simplicity. When the gases strike it, it recoils with force. This movement is mechanically connected to the bolt carrier by a steel rod. The bolt carrier, as it recoils, extracts the empty casing, ejects it, and simultaneously compresses a return spring housed in the rear. On return, the spring pushes the carrier forward. During this movement, the bolt picks up a new unit from the magazine, pushes it into the chamber, and locks into position. The complete cycle takes fractions of a second. If the selector is in a continuous mode, the process repeats until the magazine is empty or the trigger is released. But the secret wasn't just in the cycle, it was in decisions that seemed to contradict industrial logic. Kalashnikov designed the AK-47 with generous clearances, up to 2 millimeters at some points, between moving parts. For engineers trained in high-precision traditions, this was inadmissible. Precision was synonymous with quality. Tight tolerances guaranteed reliability. But Kalashnikov had observed that, in real conditions, absolute precision was a vulnerability. A thread of ice, a grain of sand, a thin layer of rust. Any minimal interference jammed tightly fitted mechanisms. The AK-47 worked the opposite way. The clearances allowed dirt to be expelled naturally during the cycle. Thick parts absorbed deformations without breaking. The gas piston system kept residue away from the chamber, and the stamped receiver, considered inferior because it was associated with cheap products, was strong enough to withstand thousands of uses, but could be manufactured on an industrial scale without requiring complex machining. When Kalashnikov presented these characteristics to the Evaluation Commission in 1947, the reaction was divided. Senior engineers questioned the tolerances. This will vibrate too much. It will lose accuracy. Others criticized the use of stamped steel. Receivers must be machined. This isn't reliable. A veteran official examined the prototype and said simply, "It looks like a peasant's tool." Kalashnikov replied, "The people using it are peasants. They need something that works, not something that looks pretty." The resistance wasn't ideological, it was technical. The military industry was structured around high-precision processes. Shifting to stamping required reconfiguring entire factories, and accepting generous tolerances contradicted decades of design doctrine. But geopolitical pressure was greater than institutional resistance. The Commission authorized field tests. Do you think this design choice was inevitable, or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing began in late 1947 and extended for months. The prototype was subjected to conditions that destroyed conventional hardware. It was buried in mud for 3 days, dug up, and used without cleaning. It worked. It was left in a snowfield for a week, exposed to temperatures below 30 degrees Celsius, and used without prior warming. It worked. It was immersed in muddy water from the Kliazma River, shaken to remove excess, and tested immediately. It worked. It was operated continuously for 2 hours until the metal glowed, then rapidly cooled in ice water. The metal warped slightly, but the mechanism remained operational. With each test, technicians recorded results. With each failure, and there were failures, Kalashnikov adjusted components. In an early phase, the return spring broke after 800 cycles. He changed the steel. The magazine occasionally jammed when fully loaded. He adjusted the geometry of the feed section. The extractor sometimes couldn't pull swollen casings caused by moisture. He increased the extractor spring force. Each revision was documented, tested, and compared with competing prototypes. There were other candidates. One used a roller-delayed system, sophisticated but sensitive. Another had a short-stroke piston system, lighter but less robust. A third was modular and ingenious, but required special tools for maintenance. All were tested side by side. All failed at some critical point. The AK-47 wasn't the most accurate, it wasn't the lightest, but it was the only one that kept working after 1,000 cycles covered in mud. The decision about receiver material was tested brutally. Engineers fabricated 2 identical receivers, one machined from a solid steel block, another stamped from folded and welded sheets. Both were installed in complete units. Both were tested 10,000 consecutive times. The machined receiver cracked after 7,300 cycles. The stamped receiver, surprisingly, lasted the full 10,000 cycles and was still functional. Stamping distributed stresses more evenly. The welds, when properly executed, were more resilient than continuously grained machined steel. This result changed the Commission's perspective. What seemed like a concession to mass production revealed itself as a structural advantage. Factories that produced truck bodies and tanks could easily adapt their lines to stamp these parts. Production costs dropped significantly compared to machined versions, and durability was equal or superior. In April 1948, after 18 months of testing, the Military Commission presented its report. Of 6 initial proposals, only 2 remained. In July, after final tests, the Kalashnikov prototype was officially recommended. The official designation would be Avtomat Kalashnikov Model 1947, AK-47. The Commission's final decision wasn't technical, it was philosophical. The July 1948 report included a sentence that revealed the paradigm shift. The Kalashnikov design does not seek to surpass its competitors in precision or refinement, but in functionality under adverse conditions. Its robustness derives not from perfect components, but from a system that tolerates imperfection. This tolerance for imperfection was the final curiosity, the concept that explained everything. For decades, mechanical engineering had followed the same trajectory: more precision, more complexity, more specialization. The principle was simple. If each part were manufactured with tighter tolerances, the final system would be more reliable. But Kalashnikov proposed the inverse. He argued that excessively precise systems were fragile because they depended on ideal conditions to function. In the real world, in cold, in mud, and in the hands of exhausted users, ideal conditions didn't exist. The AK-47's generous clearances weren't a defect accepted due to production limitations. They were a deliberate design decision. When the bolt recoiled, it had enough space for dirt particles to be pushed out of the system. When the piston was pressed by gases, it could move, even if there were accumulated residue. When the extractor pulled a casing, it had enough mechanical force to remove slightly deformed or corroded parts. The entire system was designed to degrade gracefully, to continue functioning even when conditions deviated from ideal. This philosophy extended to materials. Stamped steel wasn't just cheaper, it was more suitable for high production environments with variable quality control. One factory could produce parts with the same standards as another because stamping was a more robust process than machining. Minimal variations in steel composition or heat treatment temperature didn't significantly affect final performance. In 1949, the government formalized the adoption. The AK-47 became the standard equipment. Production began in Ijevsk in 1950. In the first 5 years, over 1 million units were manufactured. In the following 10 years, that number jumped to 5 million. And then came global distribution to allied nations and various movements around the world. But the true revolution wasn't in the numbers, it was in the principle. The AK-47 demonstrated that complexity wasn't synonymous with superiority. That simplicity, when intelligently applied, surpassed sophistication. That designing for the real world, with its limitations, its imperfections, and its imperfect operators, was more effective than designing for an abstract ideal. This lesson migrated beyond this field. It influenced agricultural tool design, vehicles for difficult terrain, and medical equipment for areas without infrastructure. Kalashnikov, while supervising initial production, didn't foresee the scale of the impact. He had solved a specific problem, but in doing so, he had articulated a universal principle. More than 75 years later, the AK-47 remains in production. It's estimated that between 100 and 200 million units have been manufactured in more than 30 countries. Variations of the original design appear in various contexts on every continent: sport shooting competitions, historical collections, and technology museums. The characteristic form, the curve of the magazine, the wooden stock, and the rectangular receiver, has become one of the most recognizable objects in modern industrial history. The technical impact was profound. The design philosophy influenced subsequent generations of hardware. The concept of intentionally generous tolerances migrated to equipment in dozens of countries. The preference for long-stroke gas piston systems became a standard in many global designs. The idea of prioritizing reliability over extreme precision redefined how engineers thought about tools intended for large-scale operation and adverse environments. But beyond its primary use, the AK-47 became a case study in industrial design. Engineering universities use its history to illustrate principles of systemic robustness. Product designers study how Kalashnikov balanced simplicity with functionality. The AK-47 narrative appears in discussions about design for low-maintenance contexts, about mass production without sacrificing durability, and about how elegant solutions aren't always the most visually refined. Mikhail Kalashnikov lived until 2013, passing away at 94. He never received royalties for the design. The creation was state property. In the last decades of his life, he gave interviews reflecting on the legacy of his creation. He expressed pride in the engineering, but also mixed feelings about its widespread use. "I invented a tool to defend my country," he said in 2006. "I cannot control where it went after that." He emphasized that the design was an answer to a technical problem, not an ideology. The final curiosity, tolerance for imperfection as a design principle, reveals something about the nature of successful engineering. Systems that work in the real world must accommodate variability. They must operate under stress. They must remain functional when conditions deviate from what was planned. The AK-47 wasn't designed for controlled environments. It was designed for chaos. And that's why, decades after more sophisticated prototypes have been forgotten, it remains. In technology museums around the world, examples of the AK-47 are displayed alongside other objects that defined eras: the incandescent bulb, the first mass-produced car, and the transistor. all share the same characteristic. They weren't necessarily the most technically advanced, but they were the most suitable for the real world. They worked. And by working, they changed how people understood what effective design meant. Kalashnikov, in 1947, while adjusting the final tolerances of that prototype in Kovrov, didn't imagine he was creating a symbol. He was simply solving a problem. How to make something that worked when everything around it failed. The answer lay in accepting that the world is imperfect, and designing honestly for that world, not against it. This honesty, more than any technical specification, is what made the AK-47 immortal. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.